Hey everybody, welcome back to physics. Today we're going to be talking about electric current. We've been spending a lot of time discussing electrostatics, which is the simplest case of electricity. Now that we understand the basics of electricity, we're going to take our charges and get them moving. The exciting thing now is by moving these charges around, we can better understand how electric circuits work. Things like the lighting in your house, your computer, your cell phone. By understanding electric circuits, we can better understand how these devices work and how they power the world around us. So, electric current. This is technically the next unit. We're moving into our unit of circuits. Current. In this lesson, we're going to be talking about what electric current is. We're going to start discussing those electrical terms that you might have floating around in your head, like amps and volts and how they interact with one another. But we really want to understand what these things are, what these concepts are fundamentally, so we can better discuss what's going on inside of our circuits. So what is current? Electric current. A good way to think about circuits and electricity is use an analogy for water flowing, right? The current of water, we could kind of imagine like how many buckets of water are passing a certain point every second. Like imagine we're looking at a river, we could see how much water is flowing and we could count the amount of gallons or the amount of buckets of water passing our point every second. The same idea goes for electric current. It's the flow of charge. Flow of charge. We want to see how much charge is passing a specific point every second. So, let's say we have, could be a wire, it doesn't really matter, but we have this avenue where current can flow. And we're looking at a specific point where I'm standing and I'm pointing. I'm like saying, hey, I want to count how much charge is passing this point every second. It's the rate at which charge flows. So if we have these charges, remember we used little q to talk about our charge. And I'm watching this point, and these charges are flowing past this point. And let's say I count that 10 coulombs of charge past that point in 10 seconds, right? That means, remember that coulombs are like buckets of charges, right? So we're actually counting the amount of charge passing a point every second. So, the electric current can be calculated by finding my rigged setup. Gotta make sure it's not wiggling. Calculated by finding the total charge passing a specific point in a given time. In a given time. That works. So once again, we're looking at a point where we're seeing how much charge is passing that point in a specific amount of time. By figuring that all out, we know the current that's flowing through that point. Pause the video, write it down, I'm going to erase. So, that's the conceptual basis of current, seeing how much charge passing a point. Here's how we calculate the amount of current for a wire for any kind of situation. So the amount of current we said is the amount of charge, the change in charge, the charge passing a point every second. So what letter do we use to denote charge in our equations? We use capital I. This equation is in your reference table. The amount of current flowing is equal to the amount of charge passing that point every second. So charge, as you all know, is measured in coulombs. The SI unit for charge is coulombs. Time, as you know, is measured in seconds. And capital I is our current. It's electric current. So current can be communicated as coulombs per second, how much charge is passing every second. So the SI unit, you can report coulombs per second, but that's not what we use in general. The SI unit is what we call an ampere. Named after Andre Ampere, which is an Italian dude. We generally, when we talk about current, we don't usually say amperes. We usually shorten that to amps. Okay. And in our equations for our units, we use capital A for amperes. And when we're talking about an amp, it's equal to coulombs per second. Okay, so again, for my example before, let's say 10 coulombs of charge past the point in 10 seconds. That would be 1 amp of current flowing through that wire, or whatever we're talking about. All right, here, I think it's time for us to work out some equations. Work out some problems. Write this down, I'm gonna erase. Let's try a question. In a wire, (22 coulombs of charge passes a point in 4 seconds. We want to determine the current flowing through this wire. 22 coulombs of charge pass a point in 4 seconds. So, using our equation, capital I for current, we can determine the amount of charge passing every second. Okay. Something I didn't mention on the last whiteboard, but current, we want to think, is this a vector or a scalar quantity? Since we're counting the amount of charge passing a point every second, this is actually a scalar quantity. Because we only want to know the amount passing every second. When we get into circuits, we will discuss the direction of the flow of charge. But it's still, like at its fundamental definition, we're just counting the amount of charge passing that point every second. It's a scalar quantity. It's not a vector quantity. The amount of charge passing in a given amount of time. So for our wire, we have 22 coulombs of charge passing a point in 4 seconds. We can plug in what we know. I equals 22 coulombs passing in 4 seconds. And this simply works out to be 5.5 amps. All right. Yeah, getting a little sloppy over here. Guess that works. 5.5 amps of current is flowing through that wire. Now, what does this mean? 5.5 amps is actually a huge amount of current passing through a wire. We're going to be discussing in a little bit the difference between voltage and amperage, potential difference and current. But current is actually what causes electric shocks to be lethal. So if you get shocked with a current that's over 10 milliamps, that's 0.01 amps, you could get painful to severe shocks. But if you get shocked with a current between 100 milliamps or 200 milliamps, that's 0.1 amps or 0.2 amps, that amount of current is actually lethal. If you get shocked with that amount of current, you could quickly die. Surprisingly, anything over 200 milliamps, you can get severe burns and unconsciousness can occur. But if there's a medical team ready to resuscitate you, you can be saved from that amount of current. So there's actually a small window where it's very lethal between 100 milliamps and 200 milliamps. Above that is still dangerous, but it's less dangerous than that window between 100 and 200 milliamps. And when I'm saying milliamps, remember that's decimals of an amp. This is 5.5 amps flowing through this particular wire. It's a lot of current. All right, let's try one more problem, and then we'll talk about some other concepts. Let's see if we can write this neater for the next one. All right. Okay. Let's say we have a current carrying wire. Carrying? Why? I don't know. Current carrying wire. Has 50 amps of current flowing. What we want to know is how much charge passes in 10 seconds. Now, once we find how much charge passes in 10 seconds, after that we want to find exactly how many electrons flowed past that point in 10 seconds. Because we know that the amount of charge we have is simply a number of elementary charges that are flowing through. So first, how much charge passes through this wire in 10 seconds? We have 50 amps, we have a time, we can solve for our Q, which is the amount of charge. Current is equal to delta Q over T. How much charge passes every second? We know it's 50 amps. Solve for delta Q. We know it's in 10 seconds. So working this out, simple multiplication, we get delta Q to be 500 coulombs of charge. So again, 50 amps is a huge amount of current, 10 seconds is a relatively long amount of time. 500 coulombs is a lot of charge passing that point. So if we have 500 coulombs of charge, 500 buckets of elementary charges, how many elementary charges is that if we counted each individual electron? Okay, so I'm going to erase this. Now part B, how many electrons pass this point in 10 seconds? How many electrons passed in 10 seconds? Okay, So thinking back to our electrostatics unit, we could figure out the total charge. We know that the total charge is 500 coulombs in this case. That total amount of charge is some multiple of elementary charges. And we're doing this. Total charge Q is equal to some number of elementary charges. This is one way to figure it out. Another way to figure it out is use page 1 of the reference table and just do dimensional analysis. Convert from 500 coulombs to a number of elementary charges. So let's work it out this way. We know that we have 500 coulombs passing this point in 10 seconds. We want to find our number, and we know the charge is 1.6 times 10 to minus 19 coulombs. Find that on page 1 of your reference table. Okay. Yes, electrons have a negative charge, but we just want to know the number passing. We're looking at the magnitudes here. So, by doing division, we find that, if you work it out yourself, the number of electrons is 3.125 times 10 to the 21st power. That's how many electrons pass. That's a huge amount of electrons. 3.25 times 10 to the 21, that was only in 10 seconds. That's how many each individual elementary charges pass that point in 10 seconds. So when we have current, when we have high current wires, things like 50 amps, we're having huge amounts of elementary charges passing that point in a given amount of time. All right. Next, we're gonna erase. So for the next thing I want to discuss, I want to discuss the difference between voltage and amperage and how potential difference affects current flowing through a wire or a circuit or anything like that. So it turns out that current, we're going to identify this and then we'll discuss what it means. Current will only flow when there is a potential difference between 2 points, 2 locations. Okay. Now, why is this the case? Why does current only flow when there's a potential difference between these 2 locations? I want to think back to that water analogy. Imagine a lake. If you have a lake with water just kind of sitting in the lake, there's no current, there's no water flowing because the bed of the lake it's equal, right? There's no reason for water to flow from one place to another. But let's say I take some of the water and I raise it up, kind of like a waterfall, right? If I lift one end of that lake up, now water is going to flow from where there's higher potential, right? Where there's higher gravitational potential energy, down to the other side. And that's analogous to what's going on here with the potential difference. The potential difference you can kind of see as the height of our waterfall. The more potential difference you have, the more of a difference you have in the height of these 2 locations. And the amount of current flowing is actually counting the amount of buckets of charge that are flowing from one end to another end. So let's draw this out. Imagine we have one location where we have a bucket of water, and we have a lower location with a bucket of water. The height here is like our potential difference, our voltage. So since we're discussing current now, or sort of discussing circuits, I'm going to use voltage interchangeably with potential difference. It means the same thing, but more often this word voltage is used than potential difference. So the voltage is kind of like our height of our waterfall, right? The more voltage you have, the higher height you have from one location to another. But if we actually watch to see how much water is flowing, how many buckets of water, how many buckets of charge is flowing past the point where we're counting it, that's what our current is. So the amount of charge that is flowing in a given amount of time is our current, where the voltage is the potential difference, the height, difference in height between these two locations. If there's no voltage, there's no reason for current to flow. Now with this analogy too, we can have a large voltage, but with a very small current, right? If we didn't have much charge to begin with, we could have a huge potential difference, a huge difference in height, but maybe not much current is flowing because there's just not enough source of charge. This is why high voltage is not necessarily dangerous, but high current is, the amount of charge that is actually flowing through. Okay. Now remember, we discussed volts, right? V is voltage in volts, and volts are given to be joules per coulomb. Okay, so if we have, let's say, a voltage of 1 volt, like 1 volt of potential difference between these two locations, if you have 1 coulomb of charge flowing from that location to another, it can do 1 joule of work on its way down to the bottom. So voltage, I want you to think of voltage in terms of energy, right? The whole point of circuits is for us to convert energy from one form to another. Let's say I have a circuit with a lamp in it, right? I want to convert the electrical energy in the circuit to the light energy of the lamp. So let's say I have 1 volt of potential difference, 1 coulomb flowing. I can deliver 1 joule of energy to that lamp. But when it comes to current, I, that's measured in amps. Technically amperes, but we often denote it as amps. And that is coulombs per second. So current is quite literally the amount of charge passing. So in order to power our devices in the future, when we start talking about circuits, we need to know how much charge is actually flowing and the potential difference between those locations. We'll get into that a bit in the future. The big idea here is understanding the difference between voltage and current. Voltage is the potential difference between the locations, the difference in height in our analogy, and current is actually how much charge is flowing between those two locations. Okay? All right. Last thing I want to discuss, and then we will be good for our video today. I'm gonna erase. So I said that current will only flow when there's a potential difference between two locations. So let's say I have location A here, location B here, connected by some conductor where current can easily flow. This is, let's say, 100 volts in this location. This is 50 volts in this location. There has to be a potential difference in order for current to flow. There is a potential difference between these two locations, right? The electric potential here is 100 volts. Here is 50 volts. So current is going to flow from high potential to low potential. This is the direction of conventional current. Now, why did I say conventional current? Here's where things kind of get a little tricky, because of some historical accidents that occurred. The way current is defined is the direction that positive charges would move in this situation. A positive charge would want to move from a high potential to a low potential. But based on our definition of our discussion of electrostatics, we know that the particles that are actually moving from one location to another are electrons. Electrons are truly flowing from one place to another in a circuit. So even though we define conventional current moving from 100 volts to 50 volts, the true direction that charges are actually flowing inside of our wire is this way. This is the direction of actual electron flow. So I guess a quick little history story. Benjamin Franklin was doing some work with circuits, and he saw that there was a flow of current from one location to another, and he had to define the direction in which the current was flowing. He kind of picked the wrong direction. He defined conventional current flowing in this direction. So because of Ben Franklin, we actually are tracking the opposite direction in which electrons are flowing. Another way to kind of look at this, if it helps you, you could just imagine which way the positive charges would be moving, but really what we're tracking is the holes in a circuit of where the electrons could be, right? Let's say we have these atoms. If electrons are flowing this way, right? Electrons are flowing this way. Really what we're tracking is the location the electron could be in, right? Let's say these three locations have electrons, and then this one moves over, and then this one moves over, and then this one moves over. What's really happening is we're tracking the hole as it bounces from one location to another. And that's because of the frame of reference that we chose. If this confuses you, don't worry about it too much. Just remember that the conventional current is the direction a positive charge would want to flow inside of a circuit. And just remember that electrons are actually flowing in the opposite direction. Something to keep in mind. Okay. So conventional current will flow in this case because there's a potential difference and there's a connection between these 2 points. Will there be a current flow in this situation? Let's say I have 50 volts here and 50 volts here. Will there be current flow? There won't be any current flow because this is our lake situation. There's no difference in height. There's no potential difference between these two locations. There's no reason for current to flow from one spot to another spot in this situation. Here is no current. Just gonna separate these two here. No current will flow here. Now, if this was 25 volts on this side, then current would flow from a higher potential to a lower potential. What about this situation? What if I have 50 volts and 25 volts? Now, current should flow in this situation between 50 and 25, but imagine that they're not connected. There's no wire between these points. It's like we're blocking our water flow. We put up a wall. Even though there's a potential difference between these 2 points, no current will flow because there's no connection between those 2 points. In our next video, we're going to start defining what a circuit is, and you're going to see that we need a connection, a connection between. We need a conductor to kind of close the loop of our circuit. If there's no conductor going from the 50 volts to 25 volts, then no current is going to flow, even though there's a potential difference. Here, we have no current flowing. All right, and with that, that's it for our introduction for electric current. Future videos, we're going to start discussing circuits, how we could build circuits, the different components of a circuit, how we could analyze circuits to make predictions, and how we could use circuits to power the world around us. But the big idea here is making sure you guys understand the difference between current and voltage and how we could calculate the electric current in a circuit if we know the charge and the time, and why current flows from one location to another. All right, hope everyone's doing well, and I'll see you in the next video.